Look at a flight map. New York to London. The route curves, not slightly, dramatically. The aircraft flies north, far north, over Canada, over the tip of Greenland, over the North Atlantic ice shelf. Then it curves back down toward Europe. On a flat map, that path looks wrong. It looks longer. It looks like the pilot missed a turn. But it is not wrong. It is the shortest possible path between those two cities, and understanding why requires you to forget everything the flat map taught you about distance. Here is what makes this counterintuitive. The Earth is not flat. You already know that, but your map is, and every flat map distorts the surface of a sphere to fit a rectangle. That distortion makes straight lines look short and curved lines look long. But on the actual surface of the Earth, on a sphere, the shortest path between 2 points is never a straight horizontal line. It is a curve, a specific curve called a great circle. And once you understand great circles, every long-haul flight route suddenly makes sense. But great circle geometry is only half the answer, because even after the shortest path is calculated, pilots sometimes fly a different path, a longer one, on purpose, and the reason is invisible. It is moving. It changes every single day, and it can save an airline hundreds of thousands of dollars per year on a single route. To understand what is actually happening, we need to start with the geometry. The Earth has a circumference of approximately 40,075 kilometers at the equator. But it is a sphere, and on a sphere, every point connects to every other point through an infinite number of possible paths. Only one of those paths is the shortest. That path is defined by a great circle, a circle whose center is the center of the Earth itself. The equator is a great circle. Lines of longitude are great circles. But lines of latitude, the horizontal bands that cross a flat map, are not great circles. They are small circles, and they are longer. Now look at New York and London on a globe. Both cities sit at approximately 51 degrees north latitude. The intuitive path, follow the latitude line eastward across the Atlantic, covers approximately 5,570 kilometers. The Great Circle path, curving north over Greenland, covers approximately 5,540 kilometers. The difference seems trivial, 30 kilometers. But that is only the geometry. Now, add the atmosphere. At cruise altitude, between 35,000 and 40,000 feet, the atmosphere is not still. It never is. Moving through it at 900 kilometers per hour, the difference between flying with the wind and flying against it is not cosmetic. It is the difference between an 8-hour flight and a 10-hour flight, between burning 60,000 kilograms of fuel and burning 80,000. And the most powerful wind system in the atmosphere sits at exactly the altitude where commercial jets cruise. It is called the jet stream. The jet stream is a fast-moving river of air circling the globe at high altitude. It forms at the boundary between cold polar air and warm tropical air, a thermal gradient that generates a pressure difference and, through the mechanics of atmospheric dynamics, a concentrated band of westerly winds. In the North Atlantic, the jet stream typically flows from west to east, from North America toward Europe. Its core wind speeds average 160 to 240 kilometers per hour. In exceptional conditions, during strong polar vortex displacement events, core speeds have exceeded 400 kilometers per hour. That is faster than many propeller aircraft can fly at all. For a jet flying eastbound, New York to London, the jet stream is a free energy source. Flying through its core adds 160 to 240 kilometers per hour to the aircraft's ground speed. A flight that would take 7 hours and 45 minutes in still air can be completed in 6 hours and 20 minutes by riding the jet stream core. Fuel savings on a single transatlantic crossing up to 15%. For an airline operating that route 10 times per day, that figure accumulates rapidly. Now, for the westbound direction, London to New York, the jet stream is a headwind. The same aircraft, the same route flown in reverse, can face a headwind of 200 kilometers per hour in its cruise band. Flying directly into it adds hours to the flight, burns thousands of additional kilograms of fuel, and costs the airline money on every single sector. So westbound pilots do something that looks strange on a map. They fly away from the jet stream. They route north, sometimes toward Iceland, sometimes toward the southern tip of Greenland, not to find a shorter path in distance, but to find calmer air, or weaker headwinds, or sometimes a secondary jet stream core that is moving in a favorable direction. The result? A flight path that covers more kilometers but takes less time and burns less fuel than the direct route through the jet stream headwind. This is the core of what flight dispatchers call wind optimization, and it is calculated fresh for every single departure. Here is how that calculation actually works. 24 hours before departure, the airline's dispatch center receives updated atmospheric forecast data from meteorological services. NOAA in the United States, the Met Office in the UK, and Eurocontrol's network manager for European airspace. This data includes wind speed and direction at every significant altitude level across the entire oceanic crossing. The dispatch system uses this data to run a route optimization algorithm. It calculates hundreds of candidate flight paths, varying in lateral track and in cruise altitude, and assigns each one a cost index, a combined figure representing total fuel burn, flight time, and operating cost. The optimal route is not always the shortest. It is not always the fastest. It is the one with the lowest cost index given the atmospheric conditions on that specific day. On some days, the optimal eastbound route cuts deep into the jet stream core, even if that takes the aircraft farther north than usual. On other days, the jet stream core is positioned unfavorably, too far south, too turbulent, or too narrow, and the optimal route stays lower and trades fuel efficiency for ride quality. On heavy weather days, entire sections of the North Atlantic are rerouted around convective systems, volcanic ash clouds, or severe turbulence forecasts. The flight path printed on the flight plan is not chosen by the pilot. It is the output of an atmospheric optimization model run by a computer against the most current meteorological data available. The pilots review it, they can request amendments, but the route they fly is a mathematical output, not a visual judgment. Now, let's look at the infrastructure that makes this possible. The North Atlantic is the busiest oceanic airspace in the world. Approximately 300 to 500 aircraft cross it every day. Unlike continental airspace, there is no radar coverage over the open ocean. Aircraft cannot be tracked in real time by ground controllers. To manage this volume safely without radar, the North Atlantic airspace uses a structured system called the North Atlantic Track System, NAT-HLA. Every day, twice per day, Shanwick Oceanic Control in Ireland and Gander Oceanic Control in Canada issue a set of organized flight tracks across the North Atlantic. These tracks are called the Organized Track System, OTS. Each track is a pre-cleared corridor at specific flight levels. Aircraft flying those tracks are guaranteed separation from other aircraft on adjacent tracks. The tracks are repositioned every 12 hours to follow the jet stream. Eastbound tracks, departing North America in the evening, are positioned to maximize tailwind from the jet stream. Westbound tracks, departing Europe in the morning, are positioned to minimize headwind exposure. Airlines bid for the most favorable tracks the evening before departure. The tracks with the strongest tailwind fill first. Airlines with less favorable scheduling sometimes accept longer routes rather than fight for a congested track. Not every aircraft flies the organized tracks. Aircraft with sufficient fuel reserves, operating at off-peak times, or flying routes that don't intersect the main crossing corridors, can file random routes, direct paths not aligned with the OTS. But those aircraft still must maintain the same separation standards and still must report their position at defined intervals, originally by HF radio, now increasingly through ADS-C. Automatic Dependent Surveillance Contract, a satellite-based position reporting system. Position reports are mandatory at every degree of longitude crossing. If a report is missed, the oceanic controller initiates a communication search. This is the invisible architecture of every transatlantic flight. Every passenger sitting in seat 32C, watching the moving map on the screen in front of them, watching the aircraft icon curve north toward Greenland. That path was not chosen by looking at a map. It was chosen by a computer analyzing hundreds of atmospheric data points, calculating cost indices for hundreds of candidate routes, and selecting the one that minimizes the total operating cost of that specific flight on that specific day in that specific atmospheric state. The Great Circle provides the geometric baseline. The jet stream provides the dynamic overlay. The organized track system provides the airspace structure. And the dispatch optimization algorithm synthesizes all three into a single flight plan. Now consider what this means at scale. A Boeing 777-300ER carries approximately 145,000 kilograms of fuel at maximum capacity on a standard New York to London eastbound departure. A fuel-optimized route through the jet stream core might require 60,000 to 65,000 kilograms of fuel block to block. A direct route flown against unfavorable winds might require 75,000 to 80,000 kilograms. The difference, 15,000 kilograms of Jet A, costs approximately $12,000 at current fuel prices. Multiply that by 365 departures per year on a single route. Route optimization is not a convenience. It is one of the most significant operational cost levers available to an airline. Airlines invest heavily in dispatch technology precisely because of this. Some operators run proprietary atmospheric modeling systems that update route recommendations in near real time as weather data is refreshed during the flight. Pilots receive revised wind data through ACARS, the Aircraft Communications Addressing and Reporting System, and can request reclearance from oceanic control if a significantly better route becomes available mid-ocean. This dynamic rerouting, changing course in the middle of an ocean crossing based on updated forecast data, is not unusual. On long Pacific crossings, it happens routinely. The Pacific presents an even more extreme version of this problem. Los Angeles to Tokyo covers approximately 8,800 kilometers on a great circle. The jet stream over the North Pacific can reach 350 kilometers per hour in winter. An eastbound flight, Tokyo to Los Angeles, riding the jet stream core can arrive more than 90 minutes ahead of schedule. A westbound flight fighting the same system can arrive 90 minutes late and burn 20,000 additional kilograms of fuel compared to a favorable day. On Pacific routes, some airlines operate polar routes, flying over or near the North Pole itself. A Los Angeles to Dubai flight via the North Pole covers approximately 13,400 kilometers. The conventional route through European airspace covers approximately 15,200 kilometers, the saving 1,800 kilometers. On a 777 or A380, that represents several tons of fuel per flight. Polar operations require special certification. Extended diversion distances from airports in Arctic regions require additional fuel reserves. Communication and navigation systems must function at high latitudes where magnetic compass reliability degrades and satellite geometry changes. But for routes where the geometry works and where the atmosphere cooperates, flying over the top of the world is faster, cheaper, and more fuel-efficient than any other option. So the next time you look at a flight map and wonder why the aircraft is curving north when the destination is clearly to the east, it is not a mistake. It is not an inefficiency. It is the output of a calculation that accounts for the curvature of the Earth, the movement of the atmosphere, the structure of oceanic airspace, and the cost of every kilogram of fuel. The shortest path on a map is almost never the optimal path in the real atmosphere, and the pilots who fly the long way around are doing exactly what the physics demands. If you want to understand what happens when that route planning fails, when the weather data is wrong, the fuel calculation is off, and an aircraft arrives over the ocean with less fuel than planned, I've covered fuel emergency procedures in full detail in another video.